Now with VXLAN flood and learn, again, the way that we would figure out this is where the destination is located is based on sending the packet as a multicast. The multicast would go everywhere, and then we would look at, well, where did the multicast come from? It came from 11153. Okay, I now know the association between the MAC address and the next hop value of the VNI. Okay, but if we look at this with BGP, the end result is still the same, that if we look at from 5K1, the show MAC address table for VLAN 22 or VLAN 11, we still know that the destination 11153 is reachable, or excuse me, this destination is reachable across the tunnel to the loopback 11153. But the difference is that we didn't need to do flooding in the middle in order to figure that out. Okay, BGP is doing an active advertisement saying, hey, this MAC is at this particular leaf. Now, if we look at the packets between the end host, so let's do capture and let's say for ICMP or ARP. Okay, and we're going to restart this. That should be 2 pipes, not 2 exclamations. Or ARP. And then let's go to server 3. And what we're going to do is clear its ARP cache. Okay, so I'm going to say ARP-D star. That's deleting the cache. Then I'm going to ping to the destination. Ping 11001. We see the ICMP packets, but we don't see any of the ARPs. Okay, let's now say that the server had a new address. Okay, so we're going to go to server 11. Or excuse me, server 3, and I'm going to change the IP address. So let's go to its network properties, and let's see, it's on this adapter here. And let's say that the address is 1100113. Okay, if we look at from 5K1's point of view, and show BGP L2 VPN EVPN, we still see the MAC address. We now go to send packet, so we're going to do a ping to 11001. Okay, we see the ICMP messages going through, but we don't see any of the ARPs going through. Okay, let's try the same thing from server 1's point of view. So let's delete the ARP cache, ARP-D star. And let's say just ARP. Let's see, I'm not sure why that didn't get captured. Oh, probably because I said or, I should have said and. ICMP and ARP. Actually, let's just say ARP. Because I think my binary logic is wrong on the filter. Okay, so let's delete the ARP cache. And you can see they're still ARPing over and over and over for the gateway. So let's say ARP-D star, and then ping to the destination. Okay, so here it says who is, so let's stop this here. It says who is 1100113. That's what the problem was. Yeah, the packet can't be both ARP and ICMP at the same time, so the filter wasn't matching. I need to say one or the other, but I'm not exactly sure what the syntax is for that. The easy way to do this in Wireshark, though, is you just right-click the packet, and then go to Apply as a filter, and then say which one you want. So and selected, and not selected, etc. Okay, so it says 110011 is trying to ARP for 11000113. Okay, if we look at where the packet is going to, though, what is the difference here between this example and the flood and learn? So notice here the packet came in from server 1. It's going to this specific MAC address. 7679. And actually, let me change router or server 3's MAC address as well to make this a little bit more obvious. So let me go to its network properties. And then advanced, locally administrator address 000000003333. Okay, and let me do the same thing for server 4 while I'm thinking of that. So later when we do the verifications here, it'll make a little bit more sense. Okay, and again, the only reason I'm doing this is just to make the show commands easier. It doesn't affect anything in the connectivity. So this is server 4. There we go. Okay, so let's try this again. Let's go to server 1. Let's restart the capture. Let's clear the ARP cache. So it's ARP-D star and then ping the destination. Okay, so it says, who has 110013? Tell 110011. Okay, so it came from all zeros 111. The destination of the ARP is a broadcast. Okay, so we don't know who owns this. It then gets encapsulated inside of VXLAN, so it goes in VNI 11111 because that's the segment that we mapped the VLAN to the VXLAN to. We then put it in UDP. Again, the port number is 4789. Then it goes inside a new outer header. Okay, so notice here it's still using multicast, even though we're also running BGP as the control plane. So BGP is not a replacement for multicast here. It's simply an optimization of the control plane. So if we run into a situation where the leaf switch does not know the mapping between the IP address and the MAC address, multicast is still needed in order to flood that traffic out to the fabric. But we'll see once we look at the layer 3 VNIs, the leaf switches are going to be creating their own local ARP cache and then trying to suppress the ARPs or basically keep them local to their access VLANs to make sure that it's not being routed over the fabric. Okay, but otherwise, if we ping, same thing, if we ping 11001113, okay, which is what I changed the IP address to, same thing should happen. So we should ARP for the destination. And it should have unicast responded to us. So it should have said, who has 11001113? Okay, tell server 1. This frame originally came from 5K1 and it was sent out as a multicast. Okay, inside of that we have the VXLAN header. Okay, so inside of that technically we have UDP, so 4789. It's a VXLAN 11111. The source is the unicast MAC address of the server, destination is the broadcast. Okay, so again, hence the term BUM traffic, it means broadcast, unknowns, and multicasts. This is a broadcast. We're encapsulating this inside of the multicast. Okay, that's why PIM is needed in the core on the fabric interfaces from the leaves to the spines. Okay, we'll see, like in the case of ACI, this happens automatically on the back end. But within the case of the BGP EVPN, we need to manually configure it because it's not an automated deployment. Okay, what is going to happen though is that when we look at our next step and we do the layer 3 routing, that these ARPs are not going to be flooded for destinations that we already know. Okay, it's only going to be for a device that we've never heard from before, or what's sometimes referred to as a silent receiver, that we would need to ARP for the destinations. Okay, so let's say now we're going to expand this over to VLAN 22 as well. Okay, so VLAN 22, we're going to say that the host reachability protocol is BGP. Okay, this config is going to go on 5K2 and 5K4. Host dash reachability, which I don't know why I didn't take that. Host reachability protocol is, or it's protocol. Host reachability protocol BGP. Okay, so this one command is the only thing that's different under the NVE interface. The rest of the config is related to the actual BGP peering. Okay, but all the leafs need to agree upon this, that host reachability protocol is BGP. Okay, this is assuming that when we look at the show run BGP, that we already have the peerings that are going to the reflectors. Okay, or technically you could do confederation, you could do full mesh, you could do eBGP. That's independent of the VXLAN config. Okay, VXLAN is just trying to do the encapsulation. BGP is the one that's doing the advertisement of the MAC address to the VXLAN tunnel endpoint mapping. As long as that network advertisement gets there somehow, that's the job of BGP. Okay, it's not the job of doing the actual tunneling of the traffic. Okay, so from 5K4, if we look at the show BGP, L2VPN, EVPN, right now we're not learning anything. Okay, so we have to generate some routes. The way that we're going to generate routes is by having the end host send traffic. That's going to cause the ARPs to be generated, the traffic to be flooded, and then ultimately we're going to generate the BGP advertisements based on that. Okay, so if we look at the show run EVPN, we're going to go to global config, say EVPN. We have the VNI is 22222 is layer 2. Route distinguisher is auto, and the route target is both auto. Okay, now what we should see again is that if we look back at the capture, and let's look for BGP, we should see that as soon as I hit enter on this last statement, 5K4 is going to generate an advertisement. Show BGP, L2 VPN, EVPN. So it looks like the capture didn't work. Let's go back to 5K2. The port must be getting hung for some reason. Interface E11, shut, no shut. Okay, so let's undo that config on 5K4. No EVPN. Okay, show CLI history, unformatted pipe to show me the last 20. So we're going to go to global EVPN, specify the VNI, the route distinguisher is auto, route target is auto. Okay, then end. Okay, once we do this, we should see a new update. BGP update message. Okay, the update is coming from the reflectors going down to the rest of the leafs. Okay, so from 72 to 5K123, from 71 to 5K123, etc. Okay, and inside this, it should be the MAC address that is talking about the final servers. Okay, so it should be advertising. It's actually going to be multiple routes in the same advertisement. So there's server 3, 3333, and then server 2 and server 4 should be in there somewhere. Okay, they may be in multiple packets. Okay, but we can see from the end result of this is that if we look at the show BGP, L2 VPN, EVPN, we know about our destination. Okay, we don't yet have it on 5K2 because I didn't add this additional config, which is going to be the EVPN. Okay, so again, this is the equivalent of like the network statement in regular BGP. If we show BGP on this on 5K2, show BGP, L2, VPN, EVPN, right now we have no routes. Okay, we add the EVPN config. Look at the show output again. Now we have our local route, and shortly we should have 5K4's route, which we do. Additionally, notice that we're learning this route twice. The reason why is that we have two different reflectors. Only one of them is being chosen as the best path, but since both of them have the same next hop value in the BGP update, the end result is that the traffic is going both directions. Okay, so if we look at specifically the show BGP L2 VPN EVPN for the address all zeros 4444, says there is two available paths. The best path is number 2. So we have path number 1 is coming from 7K2. Path number 2 is coming from 7K1. Everything is equal between the two of them except the neighbor address. Okay, this means that we would be running multipath if we had BGP multipathing on, but the lower of these values is being preferred, okay, from 11171. So this one is the best path. This is the one we're installing. But if we look at the next hop value is not changed. So since these values are equal, it means that the traffic forwarding would be the same. So essentially what happens is that a layer 2 frame comes in the access port. We look at the destination MAC address. Okay, it does a normal classical Ethernet lookup. It says show MAC address table for VLAN 22. Hey, the destination is server 4. The outgoing interface to reach server 4 is a virtual port. It's not a directly connected physical classical Ethernet interface. So it means that, hey, you need to put it inside a VXLAN. Specifically, it's going to 11154. So behind the scenes, we would have to look at what is the mapping between this VLAN and the VNI. Okay, some of the additional verifications that we have for that would be to look at the show NVE VNI. Show NVE VNI. This shows the mapping between them. Okay, so if it comes in bridge domain 22, okay, which really means VLAN 22, then you're mapping it to VNI 22222. If you have a broadcast, an unknown frame, or a multicast, you're going to go to 224.2222. Okay, so let's recap our config real quick. Let's look at the show run section NVE or VLAN or BGP or EVPN or feature. Okay, so our full config here would be, so this previous one, this was the full config of basically the flood and learn. Okay, flood and learn is simple. There's not really that much involved in it. Okay, and I'll post this text file in the file share there. Okay, so BGP EVPN is more complicated. So we need to say install feature set fabric, and we're assuming that we had this as well. So we had on both of them install feature set fabric, and we had feature NV overlay and VN segment VLAN based. Okay, so the features are kind of quirky. There's a bunch of that you need to turn on. Okay, in BGP we have these ones here. NV overlay, and then technically there's another one that is, if we show run pipe section NV, is NV overlay EVPN. Okay, those two go together. We then have the VLAN to VNI mapping. We have the tunnel interface that's specifying we're using BGP to advertise the control plane info. Under BGP, we have our actual peerings, and the address families L2 VPN, EVPN, and then we have the advertisement. So again, from an operations point of view, definitely more complicated because there's a lot more working parts of the config. But from a control plane point of view, it's more optimal behind the scenes. So when a new host comes on, it's going to actively advertise, hey, this MAC address is on this box. You're not going to have to wait to flood the traffic everywhere. You automatically know that if I receive traffic from my end host going to MAC address ABC, forward it to the VTEP 1234. Okay, questions up to this point on the BGP EVPN example. There's a question, do I know an example or a use case for BGP, for a BGP setup other than iBGP with a route reflector with the usual physical leaf spine leaf topology? Yes, there is, which we're going to look at a little bit later this afternoon. So it's going to be when you want to do inter-fabric reachability. You could also do this when you want to route traffic into ACI. So the new 2.x releases of ACI of the APIC do support EVPN as a layer 3 out config, which means that you could have like a 7K peering BGP L2 VPN EVPN to your 9K leaf, and then they would be able to exchange the control plane back and forth between the two of them. Basically the VXLAN to the bridge domain mappings, which are, from Nexus point of view, we would consider that to be the VLAN. But from the ACI point of view, we would consider it to be the bridge domain. Okay, but we'll talk about that use case a little bit in later examples.